This is a mini lecture about L'Hopital's rule. It looks like L'Hospital's rule. And you would think that this is the rule that tells you where you would go if, for instance, you break your foot. If you break le foot, you'd go to le hospital. But that's not what it is. In fact, it's pronounced L'Hopital. L'Hopital was a French mathematician, and he wrote the very first calculus textbook ever, and he put this rule in it, and it was so impressive that it got the name L'Hopital's rule. What's the deal with L'Hopital's rule? Well, before I give the rule, I want to just talk about what it's about. L'Hopital's rule has to do with indeterminate limits. Now, indeterminate limits are of the form 0 over 0, infinity over infinity. These two forms are like the templates for indeterminate limits. You've already been finding these. And we've seen in some cases that we can fix these by using, we can sometimes cancel, or we can sometimes factor polynomials and cancel to get rid of these kinds of expressions. So far we've used factoring as a great way to sometimes work. Here, I'll say factoring sometimes works. Now, sometimes, but not very often. Many, like infinity functions can have indeterminate limits where there's no factoring available. Like factoring only happens in like a really few cases. And so there are other indeterminate limits, 0 times infinity. This is another one. 0 to the 0 power. And there are other indeterminate limits. Like, is this 0? Is it 1? Is this 0? Or is it infinity? Because infinity times anything is infinity. These kinds of limits are indeterminate. Indeterminate just means vague or unclear. Like, what is it? Is it 0? Is it infinity? Do 0 and infinity cancel in this case, for instance? And you get some number, like 0 times infinity equals 1. What's going on with that? Now, in certain cases, when we see 0 and infinity as limits, and remember, infinity is not a number on the number line. Limits are numbers or infinity. Infinity means you keep on going down the number line in one direction or the other, of course, all right? However, it is the case that often when we take limits, in the end, we'll find that a limit equals something like this. Maybe your limit equals something like some number divided by 0. Now, you know that this is not defined as a number. You can't divide by 0. That's like the big rule. However, this can still make sense as a limit. Now, if the limit exists, that is the left-hand limit and the right-hand limit both give you the same thing, then when we see this, you divide a number by 0. This means as limits, and you can see this on the graph. These usually, like our last lecture, this introduces an asymptote on the graph. So this usually means plus or minus infinity, and the sign depends on the plus minus sign of the number a in the numerator. So I'm just saying, when you see 0 in the denominator as a limit, not as a number, it doesn't make sense as a number. Limits are not numbers. They're like numbers plus infinity. So when you see this and the limit exists, the left-hand limit equals the right-hand limit. They're both the same infinity, not like one's plus and one's minus infinity. Well, then this means either plus or minus infinity, and the plus minus sign depends on that number. Minus 1 over 0 in this case would be negative infinity, for instance. I'm not putting equals because these aren't actually like numbers. They don't equal necessarily, but that's what it means. If you see that you're dividing by 0 in a sense and in a limit where it makes sense, that's what it means. On the other hand, when you see that, for instance, in a limit, you've got some number upstairs and downstairs you have infinity, if this limit exists so that you have a limit upstairs that's finite, but downstairs it goes to infinity, like the limit of 1 over x as x approaches infinity, well, just like in that case, this always equals 0 so long as a does not equal infinity. And in fact, when before I wrote this, wait, I'm not going to put equals. It does equal, the limit equals that, but I'm just going to put an arrow. Plus or minus infinity like I did before. In this case, we can't have a equal to 0. So these actually make sense as limits. When you see infinity in the denominator or 0 in the denominator, with a little bit of extra reasoning, you can basically count on this one being 0. It's got the biggest number possible in the denominator, which is a really small fraction. Or it's going to be infinity if the limit exists. And similarly, you've got the smallest number possible in the denominator. Small numbers in the denominator make big fractions. Okay, these aren't indeterminate though. These are limits that are infinite or are 0. Indeterminate limits are different. Indeterminate limits look like this. Is it 0? Is it infinity? Dividing by 0 means infinity, according to what I just said. Is it infinity? Or by dividing by infinity, is it 0? So what do these mean? These are indeterminate limits. They don't necessarily mean anything yet. When you see limits of this form or the other indeterminate forms, as I've said before in class, these mean, when you see these limits, what these tell you in the problem is that more work is required. The other limits I just showed you a minute ago, a over 0, a over infinity, those are legit limits, if you can, as long as they exist. But in these cases, this is saying you've reached the point in the work where you found that the way you were going was indeterminate. Now you're going to have to do some factoring and canceling or some other sort of slick method to be able to continue. More work is required to find the limits. This is saying you are not there yet. You're not finished. So in any event, an example of this would be the limit as x approaches 1 of x squared minus 1 over x minus 1, right? The top limit approaches 1 minus 1. The bottom limit approaches 1 minus 1. This is of the form 0 over 0. But of course, we could rewrite this as the limit. This isn't really the limit. It's indeterminate the way I wrote it here. But if you rewrite this as the limit of x plus 1 times x minus 1, right? Over x minus 1. And then you cancel those two factors of x minus 1. Then this is the limit as x approaches 1 of just x plus 1. Well, that's like, let x go to 1 now. 1 plus 1. 1 plus 1 is 2. So that was a perfectly reasonable number. 0 over 0 in this case gave 2. But again, I hope that you're like, teach, this was a really special case because this was a polynomial that we could factor easily. And what if it's more complicated than that? Like you can't factor it or it's some other function. All of the other functions that you can't factor at all and cancel. And that's where L'Hopital's rule comes in. So again, L'Hopital was a fancy mathematician. He wrote, he was like a prince or some sort of like marquis or some sort of like royalty. He was also a major mathematician in the very, very earliest era of calculus. Like I said, he wrote the first calculus textbook. And he gave the rule that dominates indeterminate limits. So all of that stuff about factoring and canceling and all of that stuff is totally solved by L'Hopital's rule. L'Hopital's rule says, and again, L'Hopital is pronounced L'Hopital. I think the lo gets an accent, like stress. L'Hopital. So in any event, L'Hopital's rule says the following, okay? Could you have predicted from looking at the limit of x approaches 1 of x squared minus 1 over x minus 1, before you did the math and canceled, could you have looked at this and predicted that this would go to 2 instead of to any other number or 0 or infinity? How do you know? Could you look at this and know? Well, one thing that I can say is this. Whether or not it goes to a finite number, you can't see right away. But you could look at this right away and see that it doesn't go to infinity, right? You could see that it is not. You could see that it's not the 0, it's 0 over 0, but that it's not 1 over 0. Because you'll notice that x goes to 1 upstairs pretty fast if you're approaching 1 from either direction. Hang on a second. We actually want to take x to 1 in this particular problem. I want to go from the right-hand side. I just want to avoid there being any issues with okay, this doesn't affect the way I'm working the problem. I'm just saying it to be accurate. I just want to approach it from one side. Otherwise, it may not have a fixed plus minus sign. So we're approaching from the right. Well, as you're approaching from the right, this piece is going to approach 1. Sorry, this piece is, x is going to approach 1 faster than this x approaches 1. Because this is a square function. I'm just saying that this function has this curve, and this function x has this curve. So as you're dropping down towards 1, this is steeper. This top part approaches 0 faster than the bottom part approaches 0 because of the square. The square in there makes that top function change faster. Do you buy that? It's sliding down a steeper curve faster to get to the number 0, 1 minus 1, than downstairs. It'll get there first. This gets to 0 before this does. Well, this downstairs getting to 0 would make the thing go to infinity if the limit existed, which it does from the right-hand side. On the other hand, this one sliding down from above would make it go to 0 if it was fast enough. If it was going to 0 much faster than the denominator. All of this that I'm saying is very hand-wavy, though. You're like, what do you mean, like, faster? How can you even see that? Like, you know, well, what does faster mean in terms of functions? X squared minus 1 approaches 0 faster than x minus 1 approaches 0 as x approaches 1 from the right. What does this mean? Faster. That's talking about rate of change or slope or derivative. And so you could really argue your way through L'Hopital's rule just by thinking about it this way. Which is approaching the indeterminate, which is approaching 0 faster, the numerator or the denominator? Which is approaching infinity faster, the function in the numerator or the function in the denominator in any given limit case, right? Are they approaching at the same speed? Maybe then they cancel out and you get a number, or it equals 1 or something, who knows? I'm just saying, what does that mean? Faster means rate of change, and that of course means the derivative, d over dx. And so if you want to check if the numerator or the denominator of a fraction is going to a value faster than the other side, you have to take their derivatives. Let's see what that number is. Is it a bigger number or a smaller number? That says faster or slower. I'm trying to give you an intuitive way to say that L'Hopital's rule says that if you have a limit as x approaches some point of some function over some other function, and if that limit approaches 0 over 0, that means f of x approaches 0 and g of x approaches 0 as x approaches a, or if the functions approach infinity over infinity, one of these two forms, these are the standard forms for indeterminate limits. And as we'll see in a minute, if you have indeterminate limits of different types, well, there's lots of nice techniques in your textbook for that. You have to, however, smooth them and do algebra in some tricky way to put those functions, rewrite them in a form that their limit will look either like this or like that. But in any event, if once you've done that work and you found that you have a limit of two functions that is either 0 over 0 or infinity over infinity, well, now let's revert to what I was just saying a second ago. What makes this indeterminate is we don't know which one is going towards 0 or infinity faster. If we knew that, we might be able to know more about what the functions are doing. And what L'Hopital's rule says that's so freaking awesome is that, in fact, this limit, then the limit, in fact, the limit is given by the limit of the rate of change of the two functions as x approaches the given point. That is, you take the derivative of the upstairs function, you take the derivative of the downstairs function, and this will equal the actual limit. I'll say L, the limit. Now there's a caveat, but let's just for a minute assume that this worked. You had two functions, and so now you're looking at this, and I just want to say, this looks a lot like the quotient rule. This looks like what you wish the quotient rule was. If the quotient rule were this, it'd be so easy. That's not the derivative of f over g, right? We're not taking the derivative of this whole thing. That would need the quotient rule and you get that complicated thing. What we're saying here is simpler. We're saying the ratio of these two functions, in the end, that limit of the ratio depends on how the functions grow with respect to each other. One grows faster or slower, and that is the derivatives. And now this is amazing that this is true. My argument that this has to do with them growing faster or slower makes a lot of sense to me intuitively. It's amazing that it's actually true that that works though. It's amazing that you could apply that simple idea, take the derivatives to find the rate of change, and that actually does give you the actual number. It doesn't just tell you whether they cancel or they're 0 or something. It gives you the number that's the limit. Like we just found the limit was 2 a minute ago by canceling. Let's use L'Hopital's rule. So for that example we just did, it's such a simple example, but we already did it. So let's see that we could have used L'Hopital's rule to find the limit as x approaches 1 of x squared minus 1 over x minus 1. Now remember, we found before that this is of the form 0 over 0. If your limit is not of the form 0 over 0 or infinity over infinity, only one of those two forms, then you won't be able to use L'Hopital's rule. So again, if you have an indeterminate limit of a different form that's indeterminate, you're going to need to smooth it around using some tricks that, that are well known and not too hard to put it into this form or infinity over infinity. Anyway, we found that this was true. So by L'Hopital's rule, this limit as x approaches 1, from the right, we're going to go from the right. Well, L'Hopital's rule says this should equal the limit as x approaches 1 from the right of the derivative. The limit of as x approaches 1 of this derivative over that derivative. Notice it's not the quotient rule. Well, the derivative of x squared minus 1, the power rule says that the derivative of x squared is 2x. The power rule says the derivative of minus 1 is just 0, so there's just a 0 up there. We don't need to write it. The derivative of x is 1. And so, oops, oh my gosh, I didn't write the limit. See, we hadn't used the limit yet, so I didn't have the right to get rid of the limit symbol. We're still approaching, x approaches 1 from the right. Now we can use it. We can let x go to 1 now because we're not there's no issues of continuity or anything else there. So if we let x go to 1, 2x over 1, of course, goes to just 2. And that's what we found before. But you can see it clearly now in the limit as x goes to 1, it coming from L'Hopital's rule. Was that easier than factoring and canceling? Well, not in this case. This is like the easiest possible polynomial to factor. But in anything harder than this, any other polynomial, even if you can't factor them and cancel them, L'Hopital's rule will still give you the right answer. There's a caveat to that. Well, there's two caveats to that. Caveat number one, sometimes you use L'Hopital's rule and you get another indeterminate limit. Again. In this case, use L'Hopital's rule again. Apply LH's rule again. Eventually, you might have to apply it a few times. Eventually, you will come down to a finite limit. Sometimes, however, there are some weird cases where you'll be differentiating something and your limit, you'll just keep bouncing between indeterminate limits. This doesn't happen often, but it does happen sometimes, so I'm saying it. It'll appear to you that it's actually clearly impossible that you'll ever land on a finite limit. I can't give an example because I can't think of one because they're weird, but when they happen, they are very clear. So sometimes, in the worst cases, start over and try to rewrite your limit in a different way. I'm about to give you an example of that. That's the worst case scenario. You just have to start over. You've written it down in a way where your derivatives are in some sort of weird cycle, like I don't know exactly what right now. But I'm going to give you an example of what I mean to write it a different way. Notice that the limit of, as x approaches 1 from the right, of x squared minus 1 over x minus 1 is equal to 0 over 0. But check this out. Now, this is super tricky. Using fraction rules, this is the same thing as, I'm just going to write the same as writing the limit as x approaches 1 from the right, check it out, of 1 over x minus 1 over, in fact, hold on, I just do it even easier, of x minus 1 to the minus 1 power over x squared minus 1 to the minus 1 power. Do you buy that? Right? The minus 1 power just means you flipped it from the numerator to the denominator or vice versa. And now what is this? X minus 1 over x minus 1, as x approaches 1, from the right, approaches 1 over 0. 1 over x squared minus 1 also approaches 1 over 0. And in these two cases, since we're approaching from the right-hand limits, you can see that clearly this is infinity over infinity now. I haven't done anything differently here, right? It's indeterminate. These limits are indeterminate. They can be both 0 over 0 and infinity over infinity. They all are. All indeterminate limits can be rewritten like this. You can flip them around, and suddenly you have the opposite indeterminate limit. And on that note, this is kind of the key to how one would go about rewriting your limits to make them in the right form. So I'm just going to give you one example. Let's say that we have the function. Okay. The limit as x approaches 0 of x times the natural log of x. Okay? Well, by limit laws, that's the limit as x approaches 0 of x times the limit as x approaches 0 of the natural log of x. Of course, the limit as x approaches 0 of x is just going to be 0. But if you think about the natural log function and its graph, it looks like this. As you approach 0 from the right, let's put that there. Limit doesn't make sense from the left for the logarithm. If you approach this limit of this function, if x approaches 0 from the right, your function approaches negative infinity. right? It's going down toward negative infinity as x approaches 0 from the right. That's the logarithm function. So that's x times negative infinity. I mean 0 times negative infinity. That's like 0 times infinity. That's indeterminate. I'll just say indeterminate. So let's rewrite it. We can rewrite this in two ways. We can rewrite limit x approaches 0 from the right of x natural log of x in two ways. Probably more than two ways, but at least two ways. One, you could write the limit as x approaches 0 from the right of natural log x over 1 over x. That's what I just did before. That's like x to the minus 1, right? Written in this form, it's going to be negative infinity, because that's the limit of the natural log, over the limit of 1 over x as x approaches 0 from the right is infinity. Now it's in the right form for you to use L'Hopital's rule. Now on this rewriting, you could take the derivative of the numerator, it'll be 1 over x. Take the derivative of the denominator, it'll be like minus 1 over x squared. Do some math. It's going to turn out to be, in this case, maybe indeterminate again. Actually, now that I'm thinking about it, I'm not sure about that. I think it is. But there's another way you can rewrite this. You could also rewrite it as the limit as x approaches 0 from the right of x over 1 over the natural log of x. And you'll find that that is going to go to 0 over 0, because that goes to 0, and 1 over the natural log goes to 0 as well. 1 over negative infinity is just as much 0 as 1 over infinity. See, we rewrote this in two slick ways. One of these will work, and one of them will be hard, okay? Well, I'm guessing this one is worse, and this one's better, but I'm not sure. But one of them, you'll do L'Hopital a couple of times, and it'll turn into a finite limit, or infinity. At least it won't be indeterminate. One of them, you'll do it and over, and it'll just get complicateder and complicateder. And that's not even a word, but you'll know it. Cool? Okay, so that's L'Hopital's rule. One more thing about L'Hopital's rule is that it always works in one of these variants. Almost. I'm just going to say in calculus, this always works on indeterminate limits. And for that, we have to thank you to Bernoulli. What? Yes, in fact, L'Hopital's rule was actually proved by one of the most famous mathematicians, Bernoulli. Actually, there's a whole family of famous Bernoulli mathematicians. And one of them was hired by L'Hopital to write his textbook with him. And so L'Hopital's rule was named after the author of the textbook, but dude that he hired actually proved that theorem. Still, L'Hopital paid him to do it. It's L'Hopital's theorem, it's his book. After L'Hopital passed away, Bernoulli made a really, really big stink about this. And it didn't actually go well for him, because it kind of like was like, well, everybody was like, but he paid you for the theorem. And Bernoulli was like, yes, but my name should be on it. And everyone was like, he bought it from you. In any event, whether or not you can actually buy a theorem or art, and whether or not the naming of anything really has anything to do with that thing itself is kind of like not at issue. But the fact is that it's an amazing rule that the ratio, the limit of the ratio of the functions is the same as the limit of the ratio of their rates of change. That's so cool. That's the content of L'Hopital's rule.